Let's talk about centripetal acceleration and where circular motion comes from. So the first thing to keep in mind is that centripetal forces aren't a new type of force. The word centripetal just means pointing toward the center of a circle. So when we have circular motion, we have some force that is directed toward the center of a circle, but that force is probably some kind of force that we've already learned about, like tension or friction or gravity or a normal force, something like that. So centripetal is just a description saying that whatever kind of force it is, it points toward the center of a circle. So let's look at an example of a ball tied to a string, and you are spinning the ball around in a circle. So here's a circular path, and there's a string tied to a ball, and this ball is spinning around. So at some particular instant, there's its velocity. Now think back to our study of Newton's laws, and remember Newton's first law that says that objects in motion continue at constant velocity unless they're acted on by an external force. So if this ball is moving with this velocity vector v, and there were no forces on it, it would continue moving in a straight line at constant speed. If you want to make it move in a circle, you need to apply a force. The fact that it's moving in this circular path means that its direction is changing. It's undergoing an acceleration. And that change in direction, or that acceleration, is being caused by the tension force in the string. When you're holding onto the string, spinning the ball around, you're pulling on that string, you're applying a force to the string, that string then applies a tension force to the ball. That tension force is directed toward the center of the circle. That force is perpendicular to the velocity vector, which means that the velocity vector changes direction and undergoes an acceleration. All circular motion happens this way. It's not always a tension force, but it's some kind of force. It could be friction, it could be gravity, it could be a normal force that points toward the center of a circular path, because that redirects the velocity vector that would otherwise continue in a straight line. In the absence of this center-seeking force, the object would continue in a straight line. So you need to be pulling toward the center to change the direction of that velocity vector. So Newton's second law for circular motion looks like this. We have this force that's centripetal, directed toward the center of the circle, equals ma times the centripetal acceleration. And in the previous lessons, we learned that this centripetal acceleration has a magnitude of v squared divided by r, where r is the radius of the circular path that this thing's moving in. So this is how the magnitude of the force and the magnitude of the acceleration are related. And if you want to worry about plus and minus signs, we have some sign conventions here. If the force is toward the center, that's considered negative. If it's away from the center, that's considered positive. Oops. Force away from center. Similarly with acceleration. So with those signs, we can write Newton's second law. Like this. Sum of the radial forces equals minus mv squared over r. And most of the time, for the problems we encounter, the forces will be pointing toward the center of the circle, so they get a minus sign, and we get two minus signs that cancel out. So you just kind of recover this expression where it's plus signs on both sides of things. In the next few videos, I'll do some examples with centripetal forces.